Yeah, thank you very much for coming today and also allow me to be lazy. So I'm also having, as you, also all of you, so other like the commitments for this April. So it's kind of just a busy. So I was thinking to make my note for today's conversation, but I just unfortunately I didn't have the time and energy. So I just want to share some main references together and try to share some like the potentially possible research direction so it's also related to the Lempert theorem that we already have discussed, and still that discussion is ongoing. But rather than just understanding some of the parts of the detail, I'd like to like the initiate some of the open like the potential direction that any of us should be satisfying with imagining or also doing some like the research and study and so on. So let's just naively think about the classes of the
Actually,
bounded domain. Yeah,
I have sorry for interruption.
sure.
I had some question on the um, strong on strongly on the behavior of complex geodesics and stuff on strongly convex domain with C3 boundary. That I wanted to ask you, but I can ask later or any conversation. But you.
So that's yeah, thank you very much for that question. Please keep asking if you have any like the either the question or any like the very like the naive like the comments or remark or anything whatsoever so that we can try to develop those like the ideas together. But your like the question is about so can we understand the structure of the complex geodesic at least in the case of the strongly pseudo-convex domain with the smooth boundary. Here's what I'd like to initiate the conversation. If you look at the classes of the bounded domains, then what do we just usually assume? So let's just like the convenience, let's
Okay,
assume
my
smooth boundary.
rigorous question, if I precisely tell my question, is that suppose that there exists a real geodesic gamma t and sigma t that are converges to the same boundary point of the bounded strongly convex domain,
Mhm.
and suppose that the distance between two is less bounded above by some constant. So d sigma t and gamma t is less than some positive constant c.
Mhm. Mhm.
Then we know that every real geodesic is inside some complex geodesic in strongly convex domain with C3 boundary. So if I take gamma, then by that theorem, gamma is inside some complex geodesic.
Okay.
But but can I conclude that after some positive time t, the sigma t, which was some bounded distance of gamma, is lying inside that complex geodesic? That I wanted to ask.
So first, I do not know the answer. I have the very like a geometry like the intuition what you described, but I do not know the concrete like the answer yet. And it's very interesting question. It's about the boundary behavior of the two geodesics and if they are related in a sense that the subtraction can be controlled nicely up to some constant. Then can we say further? So it's very helpful if you share some of the main like the references to me, then I will take a look and I will give you the answer back. But so at least yeah, I didn't think about that question by myself and it's very interesting. So yeah, please just share the references, then I will take a look. I will think about it. Yeah, thanks for the question.
Okay, thank you. Thank you. Thank you.
Yeah, thank you very much. So, as already Sanjoy, when I pronounce your name correctly, hopefully. So, Sanjoy pointed out the specification of the bounded domain, classes of the bounded domain matters. So, let's just assume for a moment just a smooth boundary, and we either consider strongly pseudo-convex domain and just a geometrically convex domain, just a convex domain. And also there are other types such as the weakly, so among the weakly pseudo-convex domains, so we consider the finite type. And also there's a C-linear. And also there are other types of the classes of bounded domains for sure. And there are various ways to study those classes basically. So what I'd like to discuss, so in this like a seminar is, so we can investigate those classes by looking at the properties comparison like the equivalence of the invariant matrix, then so what is the invariant matrix? So the automorphism group is contained in the isometric group of those invariant matrix. That's the definition. It doesn't need to be exactly the same, but at least it's the subgroup. So that's the definition. I think this is very enough for all of us to like understand the definition. And so here's the first like point I'd like to twist our perspective in order to initiate the project. So what are the four classical invariant metrics? I assume all of you already know it. Carl-Theodori, right-hand metric, Kobayashi, Royden metric, and Bergman and Kähler-Einstein metric of the negative scalar curvature. Those are the cases that any automorphism becomes isometric. Is that okay with you? And there are already lots of the literatures studied these metrics for each classes of the bounded domains. So the one of the pros and cons of these metrics is that by just looking at one concretely, then we can understand indeed a lot because there are lots of the link and applications. But the cons is that it's very hard to get new result, basically. So my first like the suggestion is I'd like to add one more invariant metrics, not these four. So this is we call the Szego metric. So let me share the references first. There are two references today I'd like to share. One is this one. So all like the literatures today I share are already published so that you can just look at the published version as well. But one version is this guy. So I prefer to call it by the Szego metric. I think this is more common, but another reference is this one. So Stephen Crunch called it by the Pfefferman-Szego metric. So if you look at this reference, then you can see why he called it by the Pepperman Szego. But I think the more common one is just a convention for a moment, but they are the same thing. So so you can just search those two literatures. So you can find it from the archive. So I'd like to now add this invariant metrics in order to now think if we look at the comparison of the four invariant metrics so far we have discussed, so that we can also consider this new metric. This is also classical, but it's not considered for these four metrics, in my opinion. So that it's very much like the likely to get new result in this direction. That's one thing I'd like to add. Then, for example, if we just imagine that Lempert theorem says the coincide of the Kobayashi and Carl-Theodori in the case of the convex domain, but we do not know whether or not they really coincide for the strongly pseudo-convex. They are equivalent for sure, but other than that, we do not know. So I'd like to show you some like the open questions in this like the paper. So if you look at this guy, then so there are several things I need to say. So first, if you look at the setting, of this paper, this setting already assumes the smooth boundary, and it describes so-called Pfefferman measure. So this is the so-called Pfefferman measure, and there's a reason. Instead of you considering the Lebesgue measure, there's a reason to consider Pfefferman measure. You can take a look. But if once one define the Szego corner in the very similar way, so there should be the definition somewhere. Let me take a look. Yeah, there is a very similar definition of the Szego corner and the corresponding Szego metric, but this is not Bergman corner and the Bergman metric. So let me skip to explain the definition for a moment, and let me directly jump into the open question. So if you look at here, there should be the mention about the. So if you look at this part, it says we still do not know example of the domain which the Bergman metric and the Szego metric are fundamentally different. So, and there are clues in this paper in a sense that if you look at, so there are two clues basically. In the case of just the unit ball in Cn, Szego metric is also the Poincare metric up to some constant, dimensional constant. So it's just a coincide with the classical invariant metrics as well. And for the strongly pseudo-convex domain, it's also equivalent to the other invariant metrics. And other than that, for some investigation of the weakly pseudo-convex finite type domain in C2, I don't think Szego metric is investigated like actively. So that even the question about the difference between these two, but if you look at the description of the Szego corner, it's almost same as a Bergman corner. And the description of the Szego metric are almost quite similar, and the properties are also quite similar for well-known classes of the bounded domains. So here's the first like the point I'd like to just let Ellen think about this. Actually, I already shared my question to you before. So this is the one direction you can just think of whether or not this is very worthwhile to try. Because as I already, so I don't want to really like reveal everything other than Alan for this like a point, because this is sort of like a project, like the idea that we just share between just the two of us. But so if you look at these two references, basically, one is this one is this one. And I think this is a good reference to look at. And another one is this one, these two. So they just look at the basically strongly pseudo-convex domain with a smooth boundary. And if we search the non-literatures, they just look at most finite type in C2, and that's it. So they never look at the outside of these classes, in my opinion. So that, and their question is about, so what are the fundamental difference between the Bergman metric and the Szego metric? So then it's the geometric difference, so that it's very worthwhile to look at the curvature difference of invariant metrics outside of these domains. So if we can conclude something interesting, I think we already know actually the result. So this is worthwhile to like develop, in my opinion, so Ellen can think about this one. So I just try to resume our conversation. It's been more around now a year. So that's one thing. And now I'd like to go back to Meredith's like the perspective. So even we look at the planar domain in C1, for example. So I assume, for example, the like the annulus, for example. So character metric is non-explicit. And annulus is convex domain. So by Lempert theorem, this is coincide with the Kobayashi metric. And I didn't search, I didn't remember exactly, but for the annulus, I assume Bergman corner is also non-explicit. Because I know that there's a computation of the Bergman metric, polymer sectional curvature of the Bergman metric on the annulus. Let me just search that result. So polymer sectional curvature of the annulus. Yeah, I found it. Let me just type here.
A paper called on the Szego kernel of an annulus.
Yeah, sorry, Alan, can you say again?
Yeah. There is a paper titled on the Szego kernel of an annulus. There is a paper.
Thanks. It's no, yeah, thank you very much. I wasn't really sure, but yeah, thank you very much. So what I'd like to tell is from this paper. So this is very important, like the example as well, in a sense that this is the calculation. I just want to see just a result. Just Yeah. So this is the calculation of the annulus. It's very well known that the Bergman metric column sectional curvature can be is in the range from negative infinity to positive 2. And the annulus indeed achieves those like the limit values. So I need to look at what's the inner like the boundary and the outer boundary. And as the point approaches to either each of the boundary, it hits the possible range of the Horn sectional curvature of the Bergman metric. I don't know. It just means I didn't just check like really like seriously, but I don't know such behavior would be the same for the Szego metric. So this already tells the fundamental difference if there's any difference there, but this can be also searched. And so one of the active like the area of the several complex variable, in my opinion, is because of the importance of the Bergman corner. Very many reasons. So there are the tries to determine the explicit formula of the Bergman corner, but not many for the Szego corner. So therefore, so one can just try to compare each. So for example, so even the paper, like the Stephen Crunch is like a paper here. So it is people want to know what's the primary difference of the Bergman and the Szego corner. So he just mentioned. So let's just look at the list of the examples he just talked about. Unipole. So in this case, we already assume that we already know the Szego corner for sure, otherwise it doesn't make sense. And the next case is here. So this should be, let's see, this should be, I assume this is the strongly pseudo-convex domain, strongly pseudo-convex domain. So this case is also known about the comparison of the Szego and the Bergman corner. And this is also very important, like the example in several complex variable, and also the Bergman and the Szego corner are investigated already, at least for some cases. This is also investigated. And this is the question. This is the question. So that what one can do is that, so by looking at the concrete examples for which we know the explicit formula of the Bergman corner, then one can produce the also explicit formula of the Szego corner. So the technique could be similar, but at least this is not investigated. So that by obtaining this one, then one can compare these two, then one can conclude something interesting by investigating concretely. So this is the one direction that one can just try. And for example, I'm not sure the following. So here's a subtlety. So when we talk about the Bergman metric, the Bergman metric is coming from the complex Hessian of the Bergman corner. And when we talk about the Bergman corner, it's coming from the L2 space with the holomorphic functions with respect to the Lebesgue measure when we talk about the L2 space. And the Bergman corner has a very important property. So it has a invariance property by holomorphisms. Then in order to get that property for the Szego corner, so this is a property we'd like to keep. We'd like to keep for the Szego corner, but it's slightly different. So that's why. So in this, like the literature considers so-called the performance measure, not the Lebesgue measure. So there's a certain properties that Szego corner does not satisfy with respect to the Lebesgue measure. So that literature just changed the measure from the Lebesgue measure to the performance measure. Is it okay with you? Then the property would be similar to the Bergman corner case with respect to Lebesgue measure, and then just try to compare. However, this was just done in the case of the strongly pseudo-convex domain, not even for the finite type in situ. So even the consideration of the performance measure for the general classes of the bounded domain is still, it seems still open how to do it. Because when you look at the construction here, so when you look at the definition of this measure here, I assume you can see my cursor. So this sigma sub f is defined in this way, where this rho is the defining function. So if this rho is not strongly pseudo-convex, this definition doesn't make sense. It uses a strong pseudo-convexity. So therefore, performance measure doesn't make sense for general like the bounded domains. Whereas Szego corner is always well defined for any bounded domain in CN. So this is tricky and subtle. So let's just compare two cases. So if we have a bounded domains in CN without any assumptions, we can always define the Bergman corner and Szego corner in the classical way. And the Bergman corner satisfies the reproducing property with respect to the Bergman biholomorphisms. That's fine, but it does not satisfy for the Szego corner in that case. So that's why one changed the measure to the so-called performance measure. In that case, the property would be the same. However, in order to define the performance measure, then one need to use the strong assumption on the defining function. So only work there is just for the strongly pseudo-convex domain. So at least I do not know whether it should be extended to the nice way to the finite type in situ, or even for the convex domain, just the convex domain. This is already new, like a real new result if we can define the generalization of the performance measure and check the properties. So in that sense, this is also interesting already. Is that okay with you? And yeah, Alan, go ahead.
So my understanding is like Bergman kernel is defined using the reproducing kernels like on the Bergman
Yep.
space. That's yeah. And the definition that you have showed in the paper is you use the Pfefferman measure and define the Szego kernels. Like Szego kernels can be defined on the Pfefferman metric using the Pfefferman measure. But the Pfefferman measures are defined only on strongly pseudo-commits.
Yeah.
Now the question, you also mentioned one more point, which is my question. That is, Szego kernel can be classically defined on any bounded domains in C.
Yep.
What does it mean? Like when you mean, for example, when you say Bergman metric can be defined, it's using the Bergman space and the Bergman kernels and so on. So without Pfefferman measure, what is the idea of defining Szego kernels? Maybe I missed it, but I just want to
Yeah, I completely understood what you say. So let me try to compare two different like the properties. So yeah, so your first like the question is so whether or not Szego corner is defined for any bounded domain in CN. So let's just look at the Wikipedia's like the description of the Szego corner. So the only difference in the classical way is that so we assume it has a certain regularity on the boundary. Yeah, sorry, I might need to assume certain regularity on the boundary. It's not completely like the general like the bounded domain. So we assume each holomorphic function should be extended to the boundary. So this is not required for the Bergman corner as we already know. So in that case, we consider the Hardy space in this sense, so that we just look at the holomorphic function extend to the boundary up to continuous way. Then still we can consider the reproducing property. Then it just use the same idea as a Bergman corner to just describe the Szego corner. So up to here is the same of the description. However, so what I said is different is the following. And if you look at this description, still this measure is a Lebesgue measure. This is just a Lebesgue measure, so that we can just consider everything as the same except the boundary regularity, because we'd like to just consider this like the additional assumption. So that's why people are more interested in the Bergman corner, because Bergman corner does not require this such a like a property, like such a like the additional assumption. So, but whereas if we now look at this guy, so now we'd like to change the measure from the Lebesgue measure to the Pfefferman measure here, so that we change the sense of the L2 space first. And then this is what I'm saying. So for the, let me say, for the Lebesgue measure, this property is satisfied for a Bergman corner. Whereas for the Szego corner, this property is not satisfied any longer. And this gives the byproduct to just get the invariance property of the Bergman biholomorphisms. And such property failed for the Szego corner when we use the Lebesgue measure. That's what I'm saying. And in order to make it to be happen, so that one need to change the measure. But this changing is not required for the Bergman corner. That's what I'm saying. And this investigation was only done for the strongly pseudo-convex domain in my just a search. So even for a not finite type in situ, and not also the convex domain. So is that answer your question?
Yeah.
Then let's just further just image, and please keep like adding any comments or questions so that we can develop some interesting questions together. So but let me just make sure the list of the open question that I believe is definitely publishable if we can make the progress. Number one, so describe the Pfefferman measure for general classes of the bounded domains. In my search, it seems just done for only strongly pseudo-convex domain with the smooth boundary. Again, we already know that Szego corner is defined for the bounded domain with C2 boundary. But the description of Pfefferman measure is only case for the strongly pseudo-convex. So this must be done further for sure. So if we are just say this only works for the strongly pseudo-convex, this is not interesting. So it should be extended. That's the first question. So can we extend the framework of the Pfefferman measure for the more general bounded domains, including finite type, like a convex, C linear, and so on? That's first question. And the second question, so as open question pointed out, so we are looking for the fundamental geometric difference compared to the Bergman metric and the Szego metric. And the reason of this question is that we do not know rather than the strongly pseudo-convex domain or the finite time in situ for the concrete examples of the Szego corner. That's the main reason. So that my second question is, describe the explicit formula of the Szego corner. This is very worthwhile to investigate in the sense that in order to compare these two, then we can first look at the examples that we know the explicit formula of the Bergman corner. Then one can try to produce also the explicit formula of the Szego corner. Once we can get that, then as a byproduct, we can compare. And just a few cases are done, in my opinion, so that already explicit formula is already publishable, and comparison is worthwhile to ask. So that's my second question. Describe the explicit formula of the Szego corner if that's not is unknown. Second point. Here's my third point. So the reason to investigate the properties of the invariant matrix, and then we can just distinguish each classes of the bounded domains. Is that okay with you? So for example, the spirit of the Lempert theorem is that for the convex domain in Cn, we know Kara-Theodori and Kobayashi are the same. So this distinguish with the other the bounded domains, I mean the classes. So then the most popular way to compare or establish the equivalence of invariant matrix is so-called the uniform squeezing property. So now let me show you that part. So what I'm thinking is the following. So uniform squeezing property of the I think this is also very worthwhile to study if you're interested these types of the territory. So let me show this one. So this is most the popular the technique that we have the so-called, we assume AB uniform squeezing property if there are two basically positive numbers A and B, such that for each point we can just make the embedding inside and outside, so that you can kind of assume that so ball can be controlled inner ball and the outer ball in some way. So under that assumption, and this assumption contains lots of the classes of the domains for sure. And the important part is that four invariant matrices are equivalent depending on this A and B. So in order to establish the equivalence of invariant matrix, so the one way is just by assuming this simple definition. And there are lots of the literatures in this direction. I think you might already notice what I want to point it out. It was not investigated with respect to the Szego metric. So if you look at the Stephen Crunch the paper, so now let's look at this perspective. But my just basic question is that if we even assume uniform squeezing property, can we get, I think it could be just an easy question, but can we get something interesting in a sense that it's not just their consequence from the known the argument? And can we say something like either Szego metric is also equivalent to the other invariant metrics, for example? And can we say something different? At least it's not mentioned concretely, so that if you look at Crunch's paper, it just says, so there are uncountably many distinct, strongly pseudo-convex domains, which is not same as the ball. Then can you really say, are we really sure that Szego metric is also equivalent to the other invariant metrics? Can you really say so? It seems it could be just a consequence from the known the result, but I'm not really sure. So that this is also a direction we can ask the following. So suppose we have the certain squeezing property, then also the Szego metric behave as a similar one as the other invariant metrics. This is also other possible the question. And what else? And also it is interesting that so in Crunch's paper, she just mentioned so how to define the Szego corner in the case of the manifold, not the bounded domain, but we already know it is already problematic outside of the strongly pseudo-convex domain. So this definition should be problematic for the general complex manifold, right? We do not know outside of the strongly pseudo-convex. So even it gives so it's just awesome strongly pseudo-convexity for sure. Otherwise, this definition should not make sense already. Then what should be the reasonable definition and the extension for the manifold theory? So that we can at least look at these types of the questions when we look at the known literatures. And at least we can get something, it could be just tiny small result in the beginning, but could be interesting. And for example, this is also interesting, like the direction to think of. So one of the interesting question in the several complex variable is so-called the Chang's conjecture. Let me just state it. Chang's conjecture. You can just search. This conjecture says the following. So what we know is, in the case of unipole, all invariant metrics are the same. Is okay with you? On the unipole in CN, invariant metrics are the same. Chang's conjecture says that if the Bergman metric is Kähler-Einstein, then it must be pole by holomorphic to a pole. That's the conjecture. And this conjecture was confirmed for the strongly pseudo-convex domain with the smooth boundary. And I assume this is also confirmed for the weakly pseudo-convex domain in situ. Finite type in situ, because the reason is that, the reason is Bergman corner is non-explicit near the boundary. So by using that, they just, our non-literature, so it's quite a recent result from the people in San Diego, UC San Diego. So then what can one ask? If the Szego metric coincide with the Kähler-Einstein, right? So one can just change the perspective just a little bit. So I'm not really sure that this is really like a trivial result. So that, yeah, these are the basic the questions today I'd like to share. And depending on any of your interest, we can initiate some the projects, and we can study some literatures more detail and so on. So yeah, this today I wanna talk about. And my in my the schedule, my the semester semester here will be end around in the beginning of the May. So before then, I could be just a bit busy. So I'm just planning to write down some notes, but just I don't have the time right now. So if any of you just express your the interest of making some projects, then we can just do some the presentation for our the studying purpose together, and also we can define some common projects together as well. So this is today I want to tell and share. So if any of you have any questions or comments, let me know.
So, can I share a couple of things now? Let me try to share a couple of things. I'll share my screen.
Yeah, you can share your screen. Yep.
So basically, Ali and Bharati were trying to understand at the macro level the idea of the proof of the Lempert theorem, and then go into detail and ask each questions like why certain things are true, because we don't know all the answers.
Absolutely. Yeah,
So there are certain questions out of that. So let me share them.
sure.
So the internet is pretty bad, so I'll turn off my camera.
Yeah, while waiting, Ellen sharing. So if any rest of you two have any comments or questions, let me know.
This is really bad. It's taking a lot more time
It's
than I
fine.
thought.
Take your time.
Yeah, maybe we can request Kumi to share his slide. So his notes, then we can discuss over that.
Correct. Yeah.
It would be much better than.
Correct. So, Kuni, can you share your notes from the last sessions in the same email thread?
Okay, just give me a sec. I will then share.
Yeah, we can discuss from your notes. Maybe.
Sure. Just hang on. Found. Okay. Yep. Let's go ahead.
Yeah. So, just give me 1 minute. I'm trying one
Yeah,
last
take
time.
your time. Yep.
And
Yeah, it's been a while. I'm so sorry for that. It's just.
Maybe I will ask a question.
Sure.
So what about converse of the Lempert theorem? Is it with if you have a carothodic hyperbolic and automatically it has to be Kobayashi hyperbolic, right?
So sorry, can you repeat again? What's
So
your?
if you have a carothodic hyperbolic manifold,
Okay.
then it has to be Kobayashi, right? Kobayashi hyperbolic.
By the property of the character and Kobayashi.
Property. Yes, exactly. So what about if they're equal? Is that manifold to biholomorphic with some domain or some convex domain?
So there are currently at least two counter examples. One is symmetry by disk. Symmetry by disk is never can be exhausted by any convex subdomains. However, two invariant metrics are the same. Cartesian Kobayashi are the same. And tetra block is also another such example. And they are not convex domains, and they are I think C-linear convex domain.
Mm-hmm.
So that's an interesting. Yep.
But Kobayashi and carothodics are same in that.
Are exactly. Yep.
Okay. Thanks.
So that was very actually important question for like 2 decades ago. So people want to know if they are is that bipolar but convex domain. It turns out to be there are counterexamples. I think that question can be refined in the following way. So suppose if Cartesian and Kobayashi metrics are equivalent on a bounded domain, then what can one tell?
Equivalent, right?
Yep.
Not okay.
At the same. Yep.
Yeah.
So this condition is very strong. So if we just assume if the Cartesian metric and Kobayashi metrics are equivalent on complex manifold, this already requires the existence of non-constant bounded holomorphic function.
Oh.
This is also one possible direction, but I do not know what because it contains lots of the classes, including strong crystal convex domain, finite type in C2. But this is not exactly coincide with the bounded domain with the uniform squeezing property. I didn't assume anything related to the squeezing function, but just assume the equivalence and what can one tell? Yeah.
Okay, there is no hope that my iPad will work.
It's fine.
So, roughly speaking, I've written something extra than the thing. So basically, we'll start with the first slide where we start with. I'm really liking what I've written. I felt like I can share my story of part of it.
Okay, sure.
One last.
And that should be good for the conversation next week, by the way, so that I can just skip to prepare anything.
Okay.
I'm very happy to look at the details of this note. So I want to get some new perspective from.
Very beginning, so don't have
Mhm.
big hopes, but there are a lot of questions as well. That's
Sure.
the good part.
Okay.
Export it up.
Take your time. And while waiting, so also if any of you have any other for additional either comments or suggestions or questions or remarks or whatsoever, also let me know. And actually, I also lost on listen your like the recent works. So if you wanna, any of you wanna present your works, I'm very happy to listen and learn. Yeah, please also do it. Some like at some point.
I have the work on Anderson Lempert. So that I can present.
It's completely fine. Still, it's related to several complex variables, so I'd like to still learn it. So if you wanna present your result, then I am very happy to organize the schedule so that you can present your work, so that I can ask the questions in detail, and we can try to develop something further.
Okay, then I will send you the title and abstract. Then
Yeah, sounds
probably
perfect. Mhm.
probably in the next weekend we can I can say.
Yeah, sounds perfect. Yeah, thanks. And it also works for variety, by the way.
Kuni, can you check your email? I've sent an email. A PDF.
Okay. Let me look at it.
I hope it's.
I didn't receive any email yet, but let me try to check.
It's in the same email thread. It shows it is sent already from my end.
They try to just refresh the status of the email, but not yet.
It should be last but one email, I guess. Like, Bharati, can you also check whether you have this?
I receive it. Okay. Let's see.
No, I haven't get.
I got it. So just hang on. All right. So let me share Ellen's note. Yeah. Yeah. And thanks for being patient for the participants as well. Yeah, Ellen, go ahead.
Start from the last but one page.
You mean last page?
Yeah.
Here?
Exactly this one. Yeah.
Mm-hmm.
So we want to study like there are a lot of questions. So I'll just run through whatever our thoughts were when we were discussing I and Bharati. Bharati can also like put in this.
Excuse me.
So
Your voice is little. Can it be little louder?
okay.
Uh, for me, it's too low.
I understand.
Okay.
Can you hear me better now?
Yeah, it's much better. Yeah, thanks. Please go ahead.
Great. So, all that we know is
fine.
like, great. So the thing that we find comfortable with is like the Poincare metric and the unit disk. That's what we start with. Now, the second point is we start with any complex manifold. And if you want, we can assume it is biholomorphic to a bounded convex domain in C. And those are additional assumptions. But in complex manifold, you want to talk about metric similar to Poincare metric. So one of the metric that we are defining is Kobayashi metric. And how are we doing it? Again, by using the metric that we know in D, and then trying to use it to define a metric. So how is it done? So you take 2 points x and y. So for example, you can imagine the diagram that I've drawn below. So you start with the left ball on the left-hand side, and you take 2 points AI and BI that are mapped to the points PI minus 1 and PI. So this purple line on the bottom ball is marked to the purple line on there. So now you can collect all those sequence chain of points, chain of line segments to say, or something like that. So such that when you join all those line segments, X and Y are connected, and you take the infimum over it. So that's the idea. So you start with a Poincare metric on the disk. You look at all those images, holomorphic images, into the manifold, and in such a way they form a chain starting from X until Y path, and find the infimum over it. And that's one metric. That's the Kobayashi metric. The second thing that you want to define is the characteristic metric. And the way that is done is like you look at all holomorphic maps from the manifold to D, and that is done in a way that like the distance between the images of X and Y under the holomorphism map in the disk. When I say distance, the Poincare distance, you consider the supremum over the distance, and that gives the characteristic distance. Surprising or funny enough that while defining Kobayashi, we define as infimum over something, and for character we define as supremum over something. We might expect that character is greater than or equal to the Kobayashi, but it happens the other way. That Kobayashi is less than or equal to character all the time. That's the thing. So now this being set up, like now what happens is like we have defined two notions of distance between 2 points in a complex manifold. How? Using holomorphic map from disk to the one way is using holomorphic maps from disk to the manifold, and the other is manifold to the disk. Now the question is, can we compare them both? And Lempert's theorem says exactly that under certain assumptions. So in order to show Lempert's theorem, we need to do it in 2 parts. The first part is like characteristic is always less than or equal to the Kobayashi distance. And this is true irrespective of any domains, if I understand correctly. However, how to show that I and Bharati discussed something, but we have not like come to a concrete idea. Like we have not understood completely how that is done. That is one. The second part, which is more interesting and is specific to the assumptions of Lempert's theorem, that is the domain complex manifold that we assume is bioholomorphic to a convex domain in here. So we did that in 2 parts. How? So you take 2 points X and Y, and in the manifold, and the first part says that there exists a complex geodesic, which is nothing but holomorphic map from D to M, such that like the distance of when you say complex geodesic, what basically it does is it preserves the this point.
Just isometry.
So
Isometry.
Exactly, isometry with Poincare metric on the disk and Kobayashi metric on the manifold. That's still a question. What is the metric on N is still a question. So when we say complex geodesic, on D we consider the Poincare metric. On manifold M, what is it that you're considering? I guess it should be the Kobayashi distance. That's what we will be using later on, because that's what we are writing here. The Kobayashi distance dn of x comma y is equal to rho d of a comma b. We will come to that point. So this F complex geodesic is basically an isometry from the unit disk with Poincare metric to complex manifold with the Kobayashi distance. So what happens? This complex geodesic is basically it's telling that the infimum that are defined over all Poincare distances, images of Poincare distance, which is used to define the Kobayashi metric on the manifold M, that is in fact attained by this F. So it is in some sense, it is complex geodesic is choosing a very nice element of holomorphic maps from D to M, such that the Poincare distance and the is realized. The Kobayashi distance on the manifold is realized by the Poincare distance. So that's one point. But the question here that I had in mind is, given 2 points in a manifold, why should there exist a complex geodesic F? Thus that it contains both the points X and Y. X and Y are arbitrary points in the manifold. So this was one. This was one. This was first. I felt like this should be the first part of the second question. And the second part of part showing the other inequality is it's basically that like now we have complex geodesic connects Poincare distance with the Kobayashi distance. Now we have to somehow connect it to the connected to the mm, connected to the characteristic distance. I'm sorry, I get blank sometimes, but yeah, I'll come back. So we have to connect it to the characteristic distance. So this exactly says that there exists a p tilde, which is an element of uh, um, which is a holomorphic from manifold to the disk. Now, if you remember, in order to define the characteristic distance, we have considered all holomorphic functions from manifold to disk. So we consider such that P convolved with F is identity on D. In some sense, P tilde is like the inverse of F, and F convolved with P tilde, that is some more property of F convolved with P tilde. Now, combining this 2A and 2B, we will be able to tell given X and Y, 2 points in the manifold, we start with the Kobayashi distance. Now, since we have considered F to be a complex geodesic and X and Y to be in the image of F, we get to A and B such that F of A is X and F of B is Y, such that like this is precisely says that F is a complex geodesic. Now, what we can do is like we can write A as P tilde F because like the assumption P tilde F is identity on the disk, and we get this. And now we know that like the characteristic distance is supremum of all the holomorphic maps. So using that, we will be able to tell this is less than or equal to characteristic distance on F of A, comma B. Now, F of A and F of B are nothing but X and comma Y. So we are able to show that DM is less than or equal to CM for any 2 points. Now, this is like Lempert's theorem proof is done. But however, this 2A and 2B is a question. Now, in order to find solution of 2B is what your note talks about. How do we connect this to the extremal problems? And I and Bharati were trying to see, first of all, what are extremal problems? And in the context of this problem, what are the Banach spaces? What are the expressions for the what is the function? Bad with names.
Yeah, dual map, function, Minkowski
dual map.
functional.
What are the Minkowski functions? What are the dual? And how? So we were just trying to we were just starting with that part. And how do these Banach spaces and other things, dual maps and everything, satisfy the hypothesis so that like the solution exists, and how it's connected to existence of P tilde. So all of this part we were just starting to read, and so just wanted to tell that this is what we are doing, and there are so many questions that come in between while we are trying to do. So this is like overall understanding of the picture by us, and there are lots of questions. I'll stop.
So yeah, thanks for all those like questions, and please do not let us just clarify everything by today. So let's just try to discuss for a couple of weeks so that we can really clarify everything 100%, because now we kind of get motivated. So for the first part, even though this is already well known, but you too wanna just really check why this is the case. So let me first like share. So if you look at this reference, there should be the proposition. So I just need to check where it should be, but I just remember it just should be. So you can just found like the proposition from at least from here. Is that okay with you? That's one thing. But let me just very naively share the idea. So it's the consequence of the just a classical Schwarz lemma in the just a unit disk in C1. So the unit disk in C1, the Schwarz lemma already tells that any holomorphic function we have a decreasing property or the contraction property, and this like the inequality is a consequence from there. So because this definition of either Theodori and Kobayashi, each of them uses the unit disk in C1, and there's a clever way of using the classical Schwarz lemma in unit disk, and then this is the way. There's a way to establish this inequality for general complex manifold. That's what I remember. But I need to also check the logic, but you can find from that like the reference. That's what I did a few years ago. And as you said, so this is the interesting part of the Lempert theorem. And the part of your question is, so the difference of the definition in a sense that character metric and distance requires only single holometric map, whereas the Kobayashi distance requires a finite summation for taking this like the sum here. So the reason is, I think it's coming from the triangle inequality. So if we neglect this finite summation part, and if you just define by the one holometric function, then if one try to check the triangle inequality, it fails in general. But the reason that why this finite summation can be neglected in the case of the convex domain in planar, I mean the planar convex domain in CN, is that so also you can find from the same literature here, then because of the convexity assumption, one can always just change the numbers to just the one. So that's the reason. So convexity here plays a role. So otherwise, one need to usually consider the finite summation part here, but this actually fails. So for the general, like the complex manifold, for talking about the triangle inequality. So we say pseudo, so meaning that it could be zero, but other than that, we want to make every other properties are satisfied, like, such as a symmetric property or the triangle inequality. And in order to do so for the triangle inequality, this is needed in general. That's part of your like the question. And as you already pointed out, I totally agree with this part. And so the important part of the invariant metrics on complex manifold, and so including Carl-Theodori, Kobayashi, and let's just talk about them. So they are defined in terms of the complex structure, so that the metrics they are talking about is whether either it should be related to the just Poincare, just a metric on the unit disk in C1, or just uses, as you pointed out, it's an isometric with respect to either the Kobayashi metric or the Carl-Theodori metric. That makes sense because they only are just they rely only on the complex structure. So that we can talk about the isometric for sure, even though these are so-called the Finsler metric, so that we cannot talk about the angular information in general, rather than except the Bergman and the Keller-Einstein metric, which are Hermitian metrics, which are still invariant, but still we can talk about the isometric, we can talk about the metric on the general complex manifold. So that's why we talk about the Carl-Theodori Kobayashi, because they are the intrinsic metrics on the complex manifolds. So that also gives you another answer. So that if you have another invariant metrics, in terms of the complex structure, then we can also consider other metrics as well. But it does not need to be either exactly Kobayashi or the Carl-Theodori metric, but these are most like the popular ones. And so another important part is, in order to establish this part, this is the key, as you pointed out. This is the key, and this is very subtle. So number one, so then so there are two pieces. Number one, by using the convexity, we reduce finite number of the summation of the Kobayashi distance to just one single the term over here. So we want to neglect this summation part. For the convex domain, we already neglect this. Is that okay with you? So that part can be also found from the literature I shared, so that because of using the convexity, we don't need to care. But for the non-convex case, we should worry about this, like the part. There should be the corresponding argument. I do not know how to do it. This is already new. But yeah, so just assume that as the reference did, so we already do not have this part and just one single term here for the Kobayashi distance. In the case, so
is the statement true for non-convex domains? Lempert's theorem?
So as you know, what are the examples? Symmetry by disk, tetrablock. Those are the cases Lempert theorem still, even though these are never exhausted by the convex domains. So still, complex geodesy can be told for those like these certain C-linear convex domains, including symmetry by disk. So that's why symmetry by disk is so special. Symmetry like the polydisk from dimension greater or equal to 3, it fails, because we know they are not the same, but for dimension 2, they are the same, and we can still talk about the complex geodesy, and I think it's already classified completely. What are the complex geodesy of the symmetry by disk, at least? And I do not know other cases like a tetrahedral or whatsoever, but yeah, so that's one thing. And so that's by the way, interesting question that for the complex geodesic is the solution of the linear extremal problem of this like the principle of the duality basically. The note here, so the complex geodesic is identified is already identified as a solution of the linear extremal problem, right? So that we have a information to talk about the complex geodesic. And all those are just for talking about this theorem, basically, right? However, for this framework, as we know, we crucially uses the convexity. So it's already interesting. We already know the information on complex geodesic in the case of the symmetry by disk, but this is not convex, so that this framework fails. It's not automatically extended. So this is also a very interesting question. Then, in the case that we are in the like the bounded domains that we already talk about the complex geodesic concretely, then can we make this framework? Because we already know the answer, but the same framework is that should not hold. Then what can one tell? But so yeah, this is the key part.
In a sense, if I understand correctly, in symmetrized bidisk is an example which is not exhausted by the convex domains.
Right.
1. 2. Now, however, in symmetrized bidisk, not in the higher ones, the symmetrized bidisk, we know that the Kobayashi and Kara theory coincides. So the point is, can we give an argument, generalize some of the arguments to which will fit in for the symmetrized bidisk?
Yep.
Which can eventually be exhaust a larger class outside the convex domains. Whatever that you're handling here.
Exactly.
Okay.
So basic idea. So basic question. Can we use this also the principle of the duality to establish the complex geodesic in the case of symmetry by disk? Because then we need to overcome the convexity. And we already know the complex geodesic are already investigated, different like the literatures, different like the direction and approaches, right? It does not use this approach. So and the key point of like the part is establishing this P tilde, and P tilde is coming from this H sub T. And it turns out that so from the winding number argument, it has chosen only one possible like the zero, and all those like the settings are just for establishing this like the winding number information. That gives P tilde. So, but it uses the convexity significantly. So, but it should be not the necessary condition. As complex geodesic should be also already investigated for outside of the convex domain. So there should be the way. But yeah, so one can compare. So I didn't look at the complex geodesic like the concrete details of the symmetry by this how they investigate already, because I assume it should uses a Lempert like the theorem somewhere already. But even though it could be argument could be different, but it's interesting to establish a similar argument from this like the node that we are doing. So yeah, this is what today just I have just my very naive answers. And I can also think about the details also together, and we can discuss further next time. Is it okay with you? Any other questions you want to very naively clarify? I'm not sure that Ellen.
Yeah, I have a question.
Mhm.
The part, the second B here, given a complex geodesic, there exists a lift, right? So here is the convexity is necessary. But actually, we have used convexity in the analytic version of this argument, duality, and all those things.
I understand your question. So your question is, so in order to establish this P tilde and this proof, where did we use the convexity? That's
Yeah, exactly. How long that lemma?
I'm not sure in a following sense. This P tilde is the consequence of the so-called dual map here. And in order to talk about your map, we need to talk about your Minkowski functioner. And in that
Yes.
framework, we uses the convexity. That's what I know. So as long as this dual map makes sense of it, I don't think it's needed. So you understand what I'm talking about, right? So convexity uses to describe the Minkowski functioner and thereby dual Minkowski functioner, and dual Minkowski functioner gives the dual map in this framework. But if there's a way that we can describe dual map, so then yeah, I don't think it's needed. But for me, it's unclear how to do it.
Because it seems this is a topological property, right? The existence of the
I-
tilde.
Yeah, binding number, quite topological.
Yeah, exactly. Yeah.
Yeah, so yeah, I think this is so strong, so limited, so
Yeah.
restricted. So there should be the way to go around. But yeah, some clever like the idea should be needed.
And we have lots of doubts in the proof of the Lempert theorem. Maybe we'll discuss in the next week.
Yeah, absolutely. Yeah. So I'm very
Yeah,
happy to look at the details for
We
that.
have tried to get a full proof of the Lempert theorem without reading the prerequisite of the duality and Minkowski functional argument. So in there, we had a much confusion in the winding number, where the winding number, we talked about the winding number of H, right? So we have a function, we have a two function multiplied, we'll get a G tilde or H something.
Yep.
So we have compared the winding number of the function and winding number of the original function with the sum of the winding number of the other two functions. Right? There we had a confusions.
Yeah, we'll talk about it maybe next week.
We try to wrote regressively, but there we are not getting completely there.
Yeah. Take your time, please. So yeah,
Yeah.
so I don't need to.
Thanks a lot. Yeah.
Okay, so let me today stop the record.